Welcome to another exciting lecture. Today's lecture is dynamics. Feel free to pause the video so you can see the references that were used to draw upon the materials to be discussed today. So, vibrations. Vibrations, the study of vibrations or acoustics really started around 4,000 years BC. And an early application by the Egyptians was the musical instrument known as harps. Our present system of music is based on the Greek civilization. Pythagoras is considered to be the first person to investigate musical sounds on a scientific basis. If you think about it, if you have a guitar and you pluck a string, you will notice that string will vibrate, and you can hear the noise of that string coming from that string because the vibration frequency resonates with your ear, and so that's why you can hear it, and that's occurring through the acoustics. Okay, so that's an application of dynamics, these acoustics as an example. I also want you to pause the video and go to this YouTube video. It shows a very nice demonstration of vibration. I'll also refer to this video in the description of this video, so check it out. So free vibration, natural frequency, and mode. Let's talk about that a little bit. So free vibration, what is free vibration? It's a type of vibration in which a force is applied once, and the structure or the part is allowed to vibrate at its natural frequency. And if again, the example of the plucked guitar string, if you were to pluck it, you will see that the string will vibrate by itself with no forces applied during the motion. We call that free vibration. Occurs when the mechanical system is set off with an initial input, and then is allowed to vibrate freely. Typically, this free vibration will occur at a particular natural frequency, also known as eigenfrequency, and we'll be talking about eigenfrequency later, is a frequency at which the system will tend to oscillate in the absence of any driving or damping force. This natural frequency really depends on various parameters. It depends on the geometry. Here's a plate that has boundary conditions. It depends on the geometry, the boundary conditions, the materials, all that drives the stiffness. And then the mass of the system also matters. You can see here that there's various, here you can see various mode shapes. So what happens is that if you were to impart an initial motion, it's possible that this particular plate, as an example, can take a vibration shape that looks like this one's. Is possible. And these are the fundamental frequencies of this plate. And these are in hertz, by the way. So 12 hertz, 18 hertz, 22 hertz, 24 hertz, 26 hertz. Okay. And so when we say 12 hertz as an example, this plate is fundamental frequency in this example. If I were to set it in motion, it will likely vibrate at 12 cycles per second. So it's going to oscillate at 12 cycles per second. And so you could have other types. So if you were to have 26 cycles per second here at the bottom right, then it's likely to take this shape. So the mode shape is a motion pattern of a system oscillating at its natural frequency. And I want to point out something very interesting. The interesting part here is that every structure has a unique DNA. I want you to think about it in that manner, because each structure is going to have a particular characteristic, dynamic characteristic. And that dynamic characteristic is going to be composed of these frequencies and then these mode shapes. So think about that as we go through, but I do want to discuss what is mechanical vibration. Is a motion of a particle or body which oscillates about a position of equilibrium. And so you have this beam, for example, and it can take a first mode or a second mode or a third mode. But for it to vibrate in a first mode, it may be at a particular frequency. At a higher frequency, it may vibrate as a second mode. In a little bit higher frequency, it may vibrate as the third mode. So it is important to understand that the maximum displacements of the system from the equilibrium position is the amplitude of vibration. So this is the equilibrium position, and this is the maximum displacements of the system from the equilibrium position, and we call this the amplitude of the vibration. I also want to point out that when a periodic force is applied to the system, and I'll discuss this a little bit later, you're actually pulsating. Let's say I have a force that's applied at the middle of the beam, and it's oscillating back and forth. I'm applying that force on purpose, okay? We call that a force vibration problem because it's no longer free. What I mean with free, I pluck it, I let it go, and then the system starts vibrating either this shape, whatever shape you may want to take, but it'll vibrate as one of these shapes. And so that's a free vibration situation because I plucked it once, let it go. And in a forced vibration, I continuously continue to apply that load. And so I'm forcing the system to react with that given force. So very, very interesting and important definitions that I would like you to think about as we move forward. Why dynamics? Why do we need to look at dynamics? You know, any structure or system undergoing dynamic loading will respond differently than a system undergoing static loading. If I apply a load very slowly, there's potential that it will react statically. But if I apply sudden load to the system, it's more likely to respond dynamically. Now, that's not always the case, and we will talk about that later. Dynamics also helps us quantify the dynamic characteristics of the structure, and it can allow us to predict the response of structures under a dynamic environment. Excessive vibration can also cause excessive deformation. Take as an example car noise, vibration coming from the engine. So you could have a situation where there's a significant amount of excessive deformation. Turbo machinery, as an example, excessive vibration can cause structural failure due to high dynamic stresses. And that can be like examples as turbine blades, buildings under earthquake motion. You know, so if you were to do the laundry and you put all your clothing on one side instead of being distributed around a circle, and you run a spin on that laundry, you're going to see tremendous amount of noise, and then the machine will start vibrating. That's an example of what could happen if you have an imbalance. Such imbalances can also occur in turbine blades or rotor dynamics. You could have a blade that's not of equal mass than the other ones, and then this will then cause excessive vibrations on that particular turbo machinery. So why dynamics? Because dynamics can drive failure, and we need to really understand it. Sometimes considering the structure using static assumptions could be just sufficient. Quasi-static loads are actually due to dynamic phenomena and can remain constant for relatively long periods of time. So structural systems can be subjected to loads that actually vary over time. You're going to have these structural systems where loads are acting on it. And what is important to understand is that there are situations where the loading is very slow. And so it doesn't cause any dynamic or vibrations. And so each system really possesses characteristic times that will help you determine whether the load that you're applying should be considered static, quasi-static, or dynamic. This characteristic time is really driven by the fundamental period of free vibration. And that fundamental period that we talked about are those natural frequencies. Again, going back to that plate example, this is the natural frequency for this shape. This and the natural frequency of another shape, and so forth. These frequencies, again, this number here is in hertz, and it corresponds to the number of cycles it's vibrating per second. So thinking about that, then it's very clear that this is an important consideration to whether you should consider a structure static, quasi-static, or dynamic. Natural frequencies close to the driving frequencies can cause excitation. So if I have a natural frequency of a plate at 20 hertz, say, and I apply a loading that's close to 20 hertz in frequency, so I'm applying that load back and forth at 20 hertz, and the natural frequency of that plate is 20 hertz, then I'm going to cause something called resonance condition. And that resonance condition can cause failure. So it's very important to understand that if I'm operating near a natural frequency, the frequencies that are being applied, if they're close to the natural frequencies, it could cause failure. But if I'm operating way outside of the natural frequencies, it's possible that you can treat the system as a quasi-static system or static. system, which means that you apply the load slowly. So there are other types of analyses that should be considered. There's the harmonic loading. We'll be talking about that. Random vibration. We'll be talking about that too. Acoustics, shock, and vibration responses. So when I look at this plot here, this plot here shows the frequency range at which we typically should be looking at stuff. So when you're at a very low frequency range for a rocket, for example, you're looking more of a quasi-static response, where the loading can be applied quasi-statically to the models. When you go and move up, you start to go into sine vibrations or harmonic vibrations. Then you have acoustic noise and then shock. And we'll be discussing some of this stuff later on. What are the different types of dynamic analyses that could be conducted? You have the real eigenvalue analysis. This is basically a free vibrations problem, meaning I have that plate that I showed you earlier, and that plate is plucked. So what are those natural frequencies and mode shapes that plate is going to take? You also have the linear frequency response analyses, where there's a steady state response associated with loads that vary as a function of frequency. We also have the linear transient response analysis via direct time integration. So you're looking at the response of linear structures to loads that vary as a function of time. You have the modal dynamic transient analysis, where you look at the response of linear structures to loads that vary also as a function of time. And you may use this approach to look at jitter analysis, base drive analysis, and coupled loads analysis, things that we'll be talking about later on. You also have a shock response analysis that can be performed, and then you have the vibroacoustic or random vibration analysis that can be conducted. And so today's course, we're going to be discussing the real eigenvalue analysis, the transient response analysis via direct time integration, and I'm going to jump into modal transient dynamic analysis. And then we'll also be covering steady state response due to an input that is of a harmonic nature. I'll be discussing what harmonic really means. So consider a situation where you have a spring and you put a mass on that spring. So this spring is on stretch at the beginning. I put a mass in there, and that will cause the spring to stretch this much. So here's your little weight that we put in here. The weight is W, and it's being reacted by a tension force that causes deflection as well, and this deflection is connected to this tension force of K times del, or the stretch of the spring. K here is a spring constant, so the lower the stiffness, the more this box will move downwards, and the higher the stiffness, the more difficult it will be to stretch the spring. So I hope that's very clear what we're talking about here. And so now let me look at this equilibrium position here. I have this equilibrium position, and I'm going to call this equilibrium position location 0. And above here is the unstretched position where we started from, okay? And so if I take this structure and we were to look at the vibration of this problem, notice that from Newton's law, force equals ma. So very clearly, mx double dot, or mass times acceleration, x being the position, and the second derivative of position is really the acceleration. So that's from basic physics. So I invite you to go back and review the physics class. This force, summation of forces, should be equal to ma. And so this is what's in equilibrium. So I have the force equals ma, which is also equal to the weight of the box minus K times the stretch. You have the stretch, initial stretch, del st, and then you have the motion xm. So here's where this x comes from. But we also know that this force in the spring that's acting here is equal to K times x. You will see here that K and Kx. So we have that weight minus K times the del plus Kx, and then weight is equal to minus K times del. We found this from here, the first equation here. And so that cancels out, and so you're left with Kx. So ma equals minus Kx. Therefore, mx double dot plus Kx equals 0. And x here, x double dot, represents the second derivative of the position with respect to time. And so notice how m here is the mass of that box, and K is a spring stiffness. So we can solve this very simply. You can use wolframalpha.com. Wolframalpha.com. I don't want to spend time today in how to solve differential equations, but if the general solution for this equation is really C1 sine omega nt plus C2 cosine omega nt, where omega n is equal to the square root of k over m. So that's the general solution to this problem. Again, we've called this square root k over m omega n. X is a periodic function, and here omega n is actually the natural frequency of how this box is going to oscillate about the equilibrium position. So if I were to plug it, it's going to start oscillating, and omega n is going to tell me basically how many cycles per second it is going to oscillate, and it's going to depend on the stiffness and the mass. So I hope that's very clear what we're discussing here, and that C1 and C2 here, which is what solves, so this formula here solves this differential equation. C1 and C2 can be found from the boundary conditions, the initial conditions. And so we can look at what happens in time equals 0. So at time equals 0, this goes away. And so at time equals 0, the initial position is x sub naught. And so you can basically plug that in here. And then you can look at what happens at x equals 0 again, but look at the first derivative of x, which is the velocity. So we can also specify initial velocity. At time equals 0, this goes away, and then this gives you 1. And so you can see here how I can relate the initial velocity to the coefficient C1, and so I can solve for C1. So given the initial conditions, I'm able to solve for C1 and C2, and can fully tell you how this motion transpires. So a very important consideration, notice how the natural circular frequency of the motion depends on K and M. The higher the stiffness, the higher this omega n is. The higher the mass, the lower this omega n is. So you can see how these two play into the natural frequency of this motion. And so here, what I'm describing to you is another way of solving this equation. So if you can actually make xm as the unknown and phi as the unknown. So this is another way to solve the problem. Make two unknowns now. This also can be used to solve the differential equation that I have shown. And when you do that, you can find that xm is equal to this value here. And this happens to be the amplitude of the motion. So given the initial velocity, given the initial deflection, and given the circular frequency, natural frequency, I can tell exactly what the amplitude is going to be. And that's quite amazing. This also will tells us the phase angle that goes here, this phi here. So once I know xm, once I know phi, I know exactly how to describe this motion. Because again, omega n is equal to the square root of k over m. I also want to notice that I can calculate the period of this motion. So this is my initial position x0, and it also has an initial velocity, and then it starts oscillating. This box starts oscillating, right? And so if I'm tracking that box, it will reach a maximum value, then go to the shortest end. So here's what we're looking at. It stretches to the bottom, then goes up again, and then down and up. So this is the most stretched position, then it goes into compression. Then it stretches, then it goes into compression. And this line here represents the equilibrium state. So what I want to point out here is that this distance here between the maximum stretch to the next maximum stretch, this is called the period of this oscillation. And this period can help you calculate the natural frequency. If I know that period, then I know how many cycles per second this box is vibrating. Again, the natural frequency now can be calculated. So if this is cycling, and say this distance here is 30 seconds, then 1 over 30 seconds gives you the natural frequency. And if this distance here is 0.2 seconds, then 1 over 0.2 seconds gives me the natural frequency, and that'll be 5 hertz. That's telling me that in 1 second, the box, that box oscillated 5 times back and forth. That's really what we're talking about here when I talk about natural frequency. I want to remind you that what we're trying to do, we solve that differential equation, and this differential equation explains to you or governs the physics of how this box will vibrate about the equilibrium point. So that's what we're discussing here, is how to solve this equation. And we found that the solution to this equation is simplified with this equation here, where xm is given by this amplitude and phi is given by this. And again, the phase angle is known. We know v naught, you know x naught, and omega n. So this is fully known. So this whole motion is known. So once you know the position x, you can calculate the velocity as x dot, because velocity is equal to the derivative of the position with respect to time. And you can also calculate the acceleration, which is the second derivative of x respect to time. And this is exactly how you find the velocity and accelerations. So let's cover a little bit about force vibrations. Okay, so let's discuss that now. So in the previous example, we didn't have any forcing input that was dynamic. In the previous example, we only had a weight applied, and then we had, and the weight was coming from the box itself, and it was getting balanced by the tension in the spring. But we did not apply a force that was vibrating. In this case, what I want to do is apply a harmonic force, a periodic force. And so what I mean with applying a force, what that means is that when I apply a force, that force is oscillatory. And so think of it as you pushing and pulling continuously, and that's what we're doing here, but following a sine function. And so omega f is a frequency at which I'm applying that force back and forth, okay? And so we can see here that the equation is a very same one I had before. The only difference, I had to apply this extra force that I didn't have before. This used to be 0, so no force applied. But the rest of the equation is the same. And as you recall, it's the same idea where the weight was getting balanced by k times the stretch of the spring. So this disappears, and you get back what we had before, which is mass times the acceleration plus kx, k times x. And then you have on the right-hand side a forcing function. This is what we call the forcing function, because this force is now driving the motion of this box back and forth. In the example before, this motion was a free vibration motion, because I can pluck it a little bit to get it going. So I have an initial velocity, right, that gets it going. And so how we solve this equation here? So it's a very simple way of approaching this. First, you have to consider the complementary solution plus the particular solution. The complementary solution is fairly simple, is the solution that we discussed before. And then you have the particular solution with xm, which can be found by substituting this expression back into this differential equation. And again, I don't want to use this course to teach you how to solve this, as you have taken a differential equations class. But we can take the particular solution and substitute this into the governing equation. And when you do that, you can basically solve for xm. And once you solve for xm, you will realize here that this is known. K and M is known because that's the stiffness, that's the mass of the box, and omega F is the frequency that you're applying. So this is known. This right-hand side is fully known. So this is known, so you can find xm from this equation. And then C1 and C2, again, fall from the initial conditions that we talked before. And so notice how when omega F is close to omega N, this bottom denominator goes to 0. And so the amplitude, or xm here, from the particular solution side, goes to infinity. And so clearly, when omega f equals omega n, you have a resonant condition, meaning that the forcing frequency being near the natural frequency of the system causes significant amount of motion on this, or amplitudes on this particular example. And so you can see that here, we take the peak amplitude of the motion, and you can see it goes to infinity. And so we have resonant conditions at that point, and we call that resonance of the system. But the good news is that in a lot of situations, the vibrations are tempered by the fact that we do have natural damping. You can have dry friction, for example. You can have a situation of fluid friction or internal friction. You know, I guarantee if you take a little spring with a mass and you yank it and let it go, it'll start vibrating, and it's going to vibrate, but it's going to die out. And why is it dying out? It could be heat dissipation. The spring itself has damping within the material, or it could be the air surrounding it with drag causing it to slow down. So there's a lot of different ways this could happen. And one way that people represent this motion, this restoring motion almost, that causes everything to slow down, is C times X dot, or dash pot is one way to look at that. So you have this coefficient c, and then you have this x dot, and this term acts to basically reduce the motions as a function of time. And so if we were to add this term, and this term is usually called viscous damping, it will have, and for free vibration again, no forces, no external forces applied, just a little yank, and so let it go. So that's a free vibration problem because I'm not applying a force continuously. What we're looking at there then is this equation again, but now I have this dash pot term or this viscous damping term. And this could be due to fluid friction, it could be due to internal spring damping. But this is the equation you get, and this is your free vibration problem. And again, you can use differential equations, solutions to solve it. wolframalpha.com also works. So if we substitute e to the lambda t into this equation, we can find the solutions for this problem. Okay, and I'll just jump to the punchline. So these are the solutions you can find. You have the situation where if I define c sub c as twice m times omega n, and I call this the critical damping coefficient, so that, again, this mass, this natural frequency, this multiplication here, if I call this critical damping coefficient, if c, this coefficient c, is greater than the critical damping coefficient, then you're going to have heavy damping. So the motion will, you're going to have very little oscillatory behavior like this one. It's going to damp out a lot. So almost non-vibratory. And I invite you to think about how that could happen. If I have critical damping so that C equals C sub C, then in those cases you get non-vibratory motion again. So you don't have this box moving back and forth. All it's going to do is going to kind of die out. The motion is going to die out. Most likely it's going to follow something like this dash line and die out. The light damping situation where this coefficient C is less than the critical damping coefficient, if you have that situation, then you're going to have this vibratory motion. And it's going to die out eventually. So I wanted to point out that in a lot of situations, the motion may die with this initial velocity that you may apply or initial force. Eventually, the motion will die out. But another situation is a forced damped vibration situation where I have the same equation I had here, the one here, where I'm not applying any external force, only to just get it going back and forth. So this equation. But if I add an external force now that is of a harmonic nature, we could consider that as F naught cosine omega t. F naught is the amplitude of the forcing function I'm applying. Omega is the frequency of the forcing function I'm applying. And I will note that the solution is going to be made up by a homogeneous portion plus a particular solution. And the homogeneous part of the equation is this one here. And the particular solution to this equation is this one on the right, where x and phi need to be found. And that can be found very simply by substituting this into this top equation. But what I want you to notice here is that as time grows, as t becomes large, e to the minus whatever is here will become closer and closer to zero. And so these terms will disappear, and you will get a steady state motion driven mostly by this term right here. And so an input that's of harmonic nature as a forced vibration input is going to cause, if you have a damped vibration situation, an initial transient solution, part of the solution, plus a part that will not die out, and that's harmonic. And this is the steady state portion. So and I don't want to go into the heavy math here. The point is that, so for steady state, these x and phi can be found as here at the bottom. F naught is fully known because that's what you're applying to the system. Omega is known because you know what frequency you're applying to the system. And then C is known as the coefficient of this equation right here, the damping coefficient. And then you have omega, which is, again, the force you're applying, the frequency of the force you're applying. You have M and you have K. M is the mass of that box, and K is the stiffness of the spring. Phi, which goes into this equation, can also be found and depends on the very same parameters that are fully known. So big X, phi is known, all this stuff is known, so you know the motion of this particular system when you apply a forced vibration input. And so let's draw this a little bit. So this is the first solution we discussed. It's a free motion that you get from damping. So if you have no damping, it will continue to oscillate back and forth, but most systems do have damping, so this is what you get. When you apply a forced motion, then you're going to have a steady state part of the solution that's going to look like this. So this one here is more like the homogeneous term, and this one here at the bottom corresponds more like the particular solution part of it. So over time, when I add these two motions, I get a transient part, and then that dies out, and I will have a steady state portion that continues as a function of time. And so there is great value in studying this behavior, because this type of steady state behavior could cause fatigue, and it's also very important to study for a lot of a lot of problems in vibrations. Another interesting aspect of this problem is to really understand how much amplification am I really getting with respect to the static solution. As you know, I could apply load P on this box. I can do that statically, and that's going to cause an amount of stretch and an amount of motion. But if I'm interested in understanding how this harmonic motion that's been applied amplifies how much this box really moves, then we could look at that, and we can determine that, because X here is equal to this, and I can try to determine the amplification by dividing X by how much deflection I will have really gotten if I apply that force F statically. So if I apply that force statically, then this is X naught, and I can determine if I were to apply the motion, the force, but now in a harmonic way, what is the amplitude of, like, how much more it amplified. You can see here that if this symbol here, which I've defined as the ratio of the coefficient for damping divided by critical damping, if I look at this ratio here and I look at omega divided by omega n, and this was close to 1, and this was close to 1, this goes to 0, and the amplification is driven by this ratio. You can see that. The second observation is, assume for a second that we didn't have this coefficient C. That returns to a situation where you have no damping. And so you recover back the situation where if omega is close to omega n, the forcing frequency is close to the natural frequency of the system, then in that situation you have infinite amount of magnification. But we know that for a fact we usually have some amount of damping, so we know that will not be infinite. And so this is where this term comes into play. Now, I'm not trying to add more and more variables and confuse you, so why don't pause the video and see that what I've done is nothing more than manipulating this equation right here. What I've done is basically divided the bottom by omega n squared, since omega n equals k over m, and I used this to rearrange this equation in this manner, and I related it to what will happen if I apply that load statically. Okay, so there's great benefit in plotting this ratio as a function of omega divided by omega n, because it helps you for design purposes. So here's that plot. If I were to plot the ratio and figure out the magnification factor as a function of omega f divided by omega n, this is very beneficial because it can allows us to determine when you can treat a problem statically versus not. It can also give you information about what type of amplification you expect compared to the static solution. And so this is very helpful. So let's look at this carefully. If omega f is very small compared to omega n, then you're going to see that the amplification is almost nothing. So in other words, if you were to apply the load almost statically, that'll be good enough. And so that's very useful. It allows you to focus and figure out, do I really need to apply dynamics here, or can I get away with a static solution? This kind of plot can be very useful. Now, when you get to a frequency, forcing frequency that's close to the natural frequency, you get peak response. And again, with no damping, this goes to infinity, and we discussed that earlier. Now, if I have some amount of damping, you have quite a bit of peak response, where the peak response can be as much as 4 times if you were to apply that same load statically. And then as you increase the damping, you start to even go to a value below 1 potentially. And so that means that when I apply that load, the solution I may get, in fact, could be the load I apply could, if I have a lot of damping, could cause very little motion compared to a static solution. So in some case, if you have a heavily damped situation or system, the static solution will be conservative compared to the solution you get when you consider a dynamic model. Now, you can also notice that when omega f is much greater than omega n, so say the natural frequency of the system is 3 hertz, but the loading I'm applying is in the 50 hertz. So I'm actually pushing the system back and forth, but at 50 hertz or more. So 50 divided by 3 is quite a bit. It's much higher than this. So you will see in that situation that doesn't matter what amplitude I apply, I am not having a lot of success in causing the system to react as much. Because as you can see, x over x naught, and x naught is a static solution, x is a dynamic solution. This ratio is the magnification factor. You can see here there's a very small value, so which means that nothing much is going on. And so if I were to apply the loading statically, this force applied statically for a frequency, well, if I were to apply the load statically, I'll be already loading the system. While in fact, if I apply the same load with the frequency that's much higher than the natural frequency, the system will hardly move. And so it's important to understand that this kind of chart can help you understand the response of a system. It can help you also design for it. And so here's what we talked about, a simplification of things. If omega, the forcing frequency, is much lower than the natural frequency, you have almost a static solution. The phase angle 0 degrees is going to be 0 degrees. The response will always be in phase with the force. So the response is going to be in phase with the force. Very important. If omega is much greater than omega n, then you almost have no response in the system. And the phase angle will be such that the response is out of phase with the force. If omega is close to omega n, which is when you have resonance condition, the magnification factor is really given by 1 divided by 2 and this symbol here. And we discussed that symbol is a ratio of C, which is a damping coefficient, divided by the critical damping, where critical damping was defined earlier in the charts. So how you deal with a situation where you have a periodic force? Say you have a general periodic force. It could be a step force that varies as a function of time, but it repeats itself. You know, I don't want to go into heavy math, but I want to bring this to your attention in case you encounter that. Right now, the type of force I showed you was a very simple harmonic sine function. But you could have a situation where you have a very general periodic force. And so the Fourier series states that a periodic function can be represented as a series of sines and cosine series. And so you can take any function that's periodic and state it in this manner. And you can write this in summation symbol. And AJ and BJ can be found through these formulas. So this is going back to how you can express a general periodic function using Fourier series. How to approach that? You can apply superposition. So as you can see, the right-hand side of the equation here, mx double dot plus cx dot plus kx equals f as a function of t, where f as a function of t is a periodic function. You can see here that this periodic function is made up from these terms. And so I can superimpose the solutions. The first equation looks like this, the second equation looks like this, and the third equation looks like this. And I can find a general solution for each of this and superimpose the solution. And when I do that, I get the particular solution as the one here. The important aspect here is to understand that a periodic force will cause also a steady state response that may be a little bit complex in nature, but you can still find what that looks like. And here R is omega over omega n. J is a summation from 1 to infinity. And the AJ and BJ are fully known because that was found here in these formulas. For multiple degrees of freedom system, let's say you have 2 degrees of freedom system, these are your 2 set of equations. You assume a harmonic loading condition on the right-hand side, and then you assume a solution of this kind, a harmonic also. You plug it in, and then you're able to solve for basically the response of the system. This xj can be solved for. I won't go through that here, but the bottom line is a very similar procedure, but using matrix notation. So let's jump into finite elements, because I think that's where we can really take the idea of dynamics and really see it being applied at full-blown proportions. So that's where we want to jump into now. What is the goal is that if you have a structure that's subject to loading environments, and it could be static, it could be dynamic, I want to be able to tell you where the structure could fail. That's one potential use of this. Another potential use of this is clearances. I want to keep a particular clearance. So to solve this kind of problem, I cannot just simply use these simple formulas because the systems are a lot more complex. And so what are the driving equations that tells us about the motion of these systems? So you have the equilibrium equations of elasticity, which were previously discussed. And so this one comes from the second Newton's law, integral motion, the integral form of second Newton's law. This basically summation of forces equals ma. Think about it. So this acceleration right here, is the deflection, and these are body forces. And so stresses, you're taking the derivative of stresses respect to the position, plus the body forces equals the accelerations. And these are the deflections. So you have three equations here. I takes values 1, 2, and 3. And you have 6 stresses that are not known. So 3 equations, 6 unknowns. You have the constitutive law, which relates stress to strain. And I'm using the most general way of describing stress to strain, which is an anisotropic material. Okay, so you're used to stress equals modulus times strain. I'm just trying to point out that the stress, the 6 components of stress, is related to the 6 components of strain. And this constitutive law can be found through testing. So C is fully known. And in a simple situation, it's just the modulus of elasticity. So there you have 6 equations because I have 6 components of stress. So I should have 6 equations here. And I have 6 strains are unknown. These are the 6 strains are unknown. I also have the strain deflection relationships. The strains are related to the deflections. So I have 3 equations described here. I actually have 6 equations described here, so that's in error. And I have 3 deflections that are unknown, U1, U2, and U3. And these are the deflections in each of the X, Y, Z directions, axis. So you really have 15 equations, 15 unknowns, and they could be quite complex to solve, especially if the domain is complex, if the spatial domain is complex, like a rocket or a very complex system. This also has to be solved in a time domain. So you can see how complex this can get. The good news is that we have the finite element method. What we're after here is to discretize a structure. I have a car. It represents the car as a mass with springs and dash spots. One of the springs here could represent the tire, the compliance of the tire itself, or the stiffness of the tire itself. And then you have the dash spot, which could be representing the shock absorber. And so this is a very simple model that can be created for this car. If I have a rocket design, I could represent this as a beam with varying modulus. And so you have the mass of each of these locations. And again, that's another way to discretize this particular rocket. In airplanes, very similarly, you can represent an airplane with beams and shells. And the idea there is that with the inputs that you provide, you can solve for the response of the system. The bottom line is that discretizing the structure allows us to study these problems, these physical problems, in a more tractable way. So how do I solve these equations, which are highly complex and they're highly coupled? As you can see here, one way to solve these equations is to plug epsilon ij into this equation. And so everything here now is in terms of deflections. Then you can plug this equation back into the first set of equations. And now you have a mega gigantic 3 equations that are functional deflections, which you can then solve. And once you know deflections, you can solve for strains. Once you know strains, you can find stress. And if you can find stress and you know the strength of the material, you can determine whether the structure will fail or not. So what is the idea in finite elements is to formulate a systematic solution procedure for solving these partial differential equations over simple subdomain. And so the idea of that is that if I can discretize this domain, which is a plate with a hole, if I'm able to discretize this domain into simpler to digest domains, in this case I have little triangles that make up this structure. So I broke up this CAD model into little triangles, and my idea then is to, can I solve this PD over that little triangle? And if I can solve it for one triangle, can I then solve it for every triangle and perhaps piece the whole solution together? So there are many ways to discretize structures. In this case, a triangle was used, but you could use quadrilateral elements. If you're looking at 3D, you could use 3D elements. And if you have situations where a structure is fairly slender, is very long and slender, and maybe a beam or truss is more appropriate. Again, this course is not a finite element course, but I want to bring some of these topics to your attention. Bottom line, we're trying to solve highly complex equations, which could include dynamics, and I want to do that in the simplest way possible. Right now, not even a math book is going to help you. And so the good news is, if you're able to solve these PDs, these partial differential equations over these little triangles, and assemble all these triangles together, apply a loading condition and fix it on the other end, you can then you can actually then turn these highly complex equations into a very simple, and it's not as simple, but you are able to turn this into a more tractable way of solving it. For example, solving this analytically will be extremely hard, but if I'm able to discretize the domain into these little triangles and solve the equations for these little triangles and piece it all together, what you end up with is something more tractable, which is a discretized system. I've taken a continuous system, discretized it, and now have a mass matrix that represents the system fully. I have the acceleration term, which represents the deflections of the system. And then I have the stiffness matrix, which represents the stiffness matrix of the system. And then I have this multiplied by the deflection, and then this equal to force. And if you notice here, this looks a lot like the equation that we had here, which is 2 by 2. Mass times acceleration plus stiffness times deflections equals forcing function. And here I have damping, and we can add that here, but the bottom line here is that I can take is a mathematical miracle, because I took 15 equations that are highly coupled and turned them into a matrix of mass, stiffness, and a vector of deflections and a vector of accelerations equals to a vector of external forces applied. So this is a huge progress that we made here. Then I can now solve this equation. I'll show you how this is done. Once you solve these equations, you can post-process the results. If I want a static solution, you will turn u double dot to 0 and then get the static solution. If I want to solve this dynamically, I can do that too. So what is the end goal? We want to be able to determine whether a system breaks or not. The bigger picture perspective is that the loading environments, which could be dynamic in nature, are inputs, and they correspond to the loads that you apply to the system. So these are the loads that you really apply to the system, and these loads are applied to a finite element model. Now realize that the CAD model has been discretized. Again, this is a continuous system. We've discretized this CAD model into a finite element model. This model requires properties such as elastic properties for the modulus. You need modulus, materials, Poisson ratio, and all that. You apply the loads, and then you get the results, the finite element results. You have to post-process this finite element model after you solve it and determine where the highest stresses are. And the idea is that your predictions are validated against tests, and if you do a good job there, you're ready to figure out whether the system has sufficient margins or whether you have to go back and redesign. But the idea here is these dynamic loads are really useful in predicting the structural failure, because these serve as inputs, load inputs into the model to determine the capacity of the system to sustain those loads. Here is a finite element model for an aircraft. It has been shown here that we've discretized it into a lot of different pieces. And again, this is to show you that I can take any problem, solid mechanics, fluid mechanics, thermal conduction, diffusion, electrical conduction, and the governing equations for those systems that are given here can be discretized, and you can get a system of equations that looks like here on the right-hand side. Here's an interesting example of a temperature heat transfer problem. And I know we're not discussing heat transfer in this particular lecture, and it was discussed earlier, heat transfer, but I want to discuss it in terms of what finite elements is really doing for you. What is the problem statement we're trying to go after? We have a heat transfer equation here. The temperatures are provided at the boundary, and we want to find what is the temperature distribution within the body. So when I do that, an analytical solution looks quite complex. And just imagine a much more complex geometry. So what if I don't want to use hand calculation or closed form solution? Do I have another option? The answer is yes. I can discretize the domain into small triangles. I can solve the partial differential equation for each of these triangles, and I can piece it all together after that. So by discretizing the system, of course, I'll run into some errors, but the idea is to minimize those errors. I'll apply the material properties for this system, which in this case is conductivity, and then by doing so, I can then apply finite elements to then get into a simplified system that is a mathematical model and an approximation of the continuous system. And I've turned these complex partial differential equations into a stiffness type of term, because in heat transfer, this is more of a conductivity matrix term type. These your temperatures are unknown, and these are the functions of or heating that you apply. You can solve for temperature that way by inverting the K matrix. And you can post-process the results and then find the temperatures more automatically. So what finite elements has done for you is found a systematic method of turning any partial differential equation into a linear algebra type problem, which allows you to solve for the unknowns and which allows you to solve for the variable of interest in a simple way. And that is easy for you to then even visualize. So let's step into direct time integration. That is the topic that I want to hit next, and I'm going to start talking about dynamics now. So take an example of a 1D elastic bar of length of 200 inches. So this 200 inches length, the cross-sectional area is 1 inch squared. This is a steel material with modulus 30 MSI. The density is given to you, and we've converted that into consistent units so we can solve it. And this particular bar is clamped on the left-hand side. We also have a constant, instant, so it went from 0 to 1,000 pounds, instant load applied, that's constant over time. So the bar has no deflection or velocity at time equals 0, but we have applied the impulse and maintained that constant over long time. And again, we could solve this in an exact way using the Fourier series approximation to this function. But in this problem, we're going to use finite elements. And I'm going to show you in a very general way how you can discretize this differential equation that corresponds to this bar. So what we want to do is to discretize this continuous system. And so we will then do that now. So here is the differential equation that corresponds to the elastic bar. This is called the strong form of the problem, or the governing equation to the problem, which is the mathematical representation of the behavior of this bar subject to these loading conditions. So given the loading applied, E is the modulus, A is the deflection, U is the axial deflection as a function of x, and it's also a function of time. And then I could have a distributed load applied that's also a function of x and time. And that's equal to m, the mass, times acceleration. In this case, it's density times the cross-sectional area, times the second derivative, partial derivative of u respect to time. So what is the first step? And again, I don't want you to get hung up on the mathematics, but I'm trying to show you that I can take any equation and turn it into discretized form. I will show you the fundamentals of how that's done. That does not mean that this particular lecture is meant to teach you how to do that. For that, I have other lectures in my YouTube channels that go into that into more detail. But for now, the approach that's typically used is to put everything on the left-hand side, multiply by a weight function v, and integrate it over the domain. And what this allows me to do is to take this error, so if I move everything to the left-hand side, and approximate u over a domain. In this case, I want to approximate it over a domain. Easy to solve domain. What I want to do is minimize the error by making it orthogonal to v. And v is a weight function we're selecting. So by doing so, I'm integrating this over the domain and On average, I want my error to be equal to 0. So this is the first step in trying to solve these partial differential equations in an approximate way. So the method we're discussing here has a name. It's called the weak form Galerkin. You can then integrate by parts this term, and we've done that. So if you integrate this term by parts, and I invite you to pause the video at this point, look at a mathematics book and remember how to integrate by parts. And the idea is to put one of these derivatives over the other one so that we can then apply the finite element method. And while we're doing that, we're trying to decrease the continuity requirements on the deflection u. And that helps us because suppose for a second, I want to approximate u, this deflection u, with a linear function. If I do that, you can see that the second derivative of a linear function goes to 0. And I want to be able to approximate solutions with a linear function because I think that's not a bad approximation. As a consequence, by integrating by parts, we have weakened the continuity requirements. And now by doing so, the derivative of a linear function u gives me a constant, so it doesn't go to 0. And I retain the ability to use an approximation for u as a linear function. Again, all we're trying to do is to take this partial differential equation and discretize it. And to discretize it, we have to approximate u over a simple domain. But I'm going to also approximate u over that domain using a linear function. That's one possible approximation. But if I were to make that happen, the second derivative of a linear function goes to 0. So that's why we're doing this integration by parts. It's a trick. And so I invite you again to pause the video, go to math book, look how to integrate by parts. And when you do check that, you will see that you will get exactly what I have here. Welcome back. And if you did that and you were able to get it, congratulations, because you're the king of integration by parts. And if you stuck with us and you didn't pause the video, I don't think less of you, but I hope you understood the steps we are talking about here. So this is a weak form Galerkin. This is the governing equation now for that bar, that particular domain we're focusing on. We call this a weak form of the problem. So now this is a continuous system, but I want to discretize the system into two elements, two domains, two subdomains. So I want to remind you what we did. We have a continuous system. We discretize it into finite elements, finite number of domains, which is the reason it's called finite elements, because I have taken a continuous domain and turn it into a finite number of subdomains, and each of these subdomains are called elements. In this case, I've taken a continuous system and turned that into two elements. So I've simplified, I've discretized the domain into two elements, and I want to approximate the deflection u, axial deflection u across this bar with a linear approximation across each of these elements. If I look at a general bar, so say the bar goes from xi, position xi to position xj, I could approximate the deflection u along this bar. I'm going to do it in the following manner. I'm going to use separation variables. So I'm going to approximate u as equal to be u as a function of time, u at this node as a function of time, times the shape function. This function here is an approximation function that tells me how u varies across this bar. I also have this deflection uj, which corresponds to the deflections at this node. And this is only a function of time. Here is the shape function that's fully known. You can see xi and xj is fully known. We know the coordinates of this bar. So I know xi, xj, I know all of this. So ni and nj are fully known, and they're a function of x, and that just tells you how u bar is being approximated from xi to xj. The only unknowns are really ui and uj at each of these node boundaries. So if I take this vector n, bold, and make it ni and nj, make it part of n, and ui and uj is part of u, then you can see that n bold is a matrix of shape functions, while u, I, and uj are the vectors that correspond to the unknowns at these nodes, and they're only a function of time. So I have actually simplified the problem even further. I've done separation variables on the time domain and the spatial domain. And on the spatial domain, I have selected a linear approximation across. You can see here that this works really well. You can actually find different approximations across this linear element. We call this linear element because the approximation of this deflection over this domain is linear. So what is the next step in this process? And so we've used separation variables. U, which is a function of x and time, has been divided into two aspects. We have the shape function, which tells me how u spatially varies over a single element, which I chose a linear approximation. And u is the unknown deflections, which only depend on time and are located at the nodes. I don't know the nodal deflections. So what are we talking about here? We're talking about this continuous system here. I've discretized into two elements. And so the only unknowns then is the unknowns at the nodes 1, 2, and 3. And if I know the node value at 2 and 3, then I know how the deflection varies along the elements. If I know the deflection at 2 and I know that the deflection at 1 is 0 because it's clamped, then I know exactly how the deflection varies along the elements. And so that's how that n function is coming to play. This n is allowing me to understand the variation of the deflection across the elements. And so the only unknown is really at the nodes u bold as a function of time. So if I use this and I were to substitute that into the weak form that I have developed earlier, you have to make these derivatives occur. One thing I did not explain before is that we're going to make the error, which is all this stuff without the v's, orthogonal to v by selecting v as the approximation n bold, the shape functions that we talked about. So I'm going to substitute for v n bold transpose, and for deflections, I'm going to substitute n bold, u bold in here. And when you do that, you get this simple, more simplified version. I have rho A, the density times area, and the vector of shape functions transpose times the vector of shape functions, u double dot, and you can see here, plus EA, B bold transpose times B bold U, minus the loading applied, n bold transpose minus q bold. And this one can also vary as a function of time, the loading applied. So I'll then discretize this continuous system by substituting these discretizations I came up with. Note that here u is a continuous, can vary continuously, while here we have discretized the domain. And you can see here that the derivative of u respect to x, which is required in this equation, is really the derivative of n bold respect to x, because u does not depend on x, so that's easy. I'm calling this b bold for simplification, so that's why you see a b bold there. You also have the second derivative of u respect to time that needs to be calculated. N bold does not depend on time, so that's easy. That's only u double dot that goes there. And you're basically done. So you can substitute all this stuff and you get this here. And again, I'm not pretending that without you taking a finite element course, you will know exactly all the steps I'm discussing. But what I'm trying to show you is that when you expand everything and you work it out, you actually get a very simple mass matrix that looks like this. You get a stiffness matrix that looks like this. And then you get the forcing functions on the right-hand side that are the ones you specify that drive the motion of the system. And so this actually is the discretization of this. The single element here has this mass matrix and this stiffness matrix. And why is 2 by 2? Very simple. A single element here has two nodes. There's only 2 degrees of freedom. And so that's why you see here a 2 by 2, because the deflections are unknown for that single element, are the deflections are not known at either side of that element. So here's node 1, and those are the only unknowns. So that you have basically a 2 by 2. That makes sense. And so I have that. I have it for a single element. And the beauty of this is, and the point I'm trying to make over and over, is that I have taken very complex, fairly complex differential equation, which varies where u, the deflection u, varies spatially, but also it varies in the time domain. And I've shown you how this was turned for a single element, has been turned into a simplified linear algebra type problem. For a quadratic element, if I were to use a more advanced element where I approximate the deflections across the element using a quadratic approximation, then you will have a 3 by 3. it will be more accurate. But the bottom line is we need to figure out a way of solving these equations. So let's go back to this classic dynamic problem. I've shown you how I was able to turn in a differential equation into a simplified problem where it looks like a linear algebra problem. So here is a bar with the load applied as a function of time. And I've discretized the domain into two elements. And so I have a total of 3 degrees of freedom. This one right here is known because it's always fixed. So for element number 1, I have this as a mass matrix and this as a stiffness matrix. For element number 2, I have this as a mass matrix and this as a stiffness matrix. I can then put these two elements together. I can assemble these two elements so they have a common node here, and the common node is 2. And so the common node is 2 here. You can see that there. That degree of freedom is shared right across the two elements. So this represents for element number 1. This represents for element number 2. I can assemble that together. And what I have now is a fairly simple system now. This is your mass matrix. This is your vector that contains the only unknowns now, which is U1, U2, U3, the accelerations, plus the stiffness matrix, and the deflections are unknown. And these forces are applied, so they're known. What I want to point out here is that we took a continuous system here where U varies across the whole thing. And I've turned that into a discrete system where the system only depends on the unknowns at 1, 2, at nodes 1, 2, and so therefore I have simplified the system quite a bit with 2 elements and 3 nodes, 3 degrees of freedom. And so this is what I got. And so this is the important thing I really want you to understand. So how we go about solving this problem? So we've simplified the system into a mass matrix, the stiffness matrix, and now we need to figure out how to solve the problem. So to solve these equations here, we're going to have to use Taylor series expansion. And I know everybody here knows what Taylor series expansion looks like. What we're going to do is we're going to find an approximation to t plus delta t. T, we're looking at the time t, so time step t, and we're looking around that time step. And so I'm going to make an approximation of this. So t plus delta t, the deflection at t plus delta t is approximately equal to the deflection at time step t plus the velocity at time t, delta t, plus 1/2 delta t squared times the acceleration. So all I've done here is an approximation of that deflection looking at a time around t. I'm also going to do a Taylor series expansion, but a simpler kind for the velocity. So t plus delta t is approximately equal to u dot time plus u double dot time times delta t. So this, hopefully this is something you can pause the video and kind of see if you can get it on your own, because we haven't done anything here that's really new. I'm going to make some modifications to the expressions above, and I know it's going to look very strange, but I think you will get it if you stick with me. So this first term right here has been approximated, and I kept everything except here. I've done a little approximation. So I've taken the acceleration term and made it times 1 minus beta 2 plus beta 2 times u double dot t plus delta t. So we recover the expression above if I set beta 2 equal to 0. You can see that here. If I set beta 2 equals to 1, this goes away and I get this term right here. So these are just mere simplifications that one, or basically an expansion or generalization of Taylor series expansion. And what we're really doing is taking this term and making it an approximation of the present over the future. So it's somewhere in between is what we're doing here with the acceleration term. And we can do the same thing with the second equation here, the velocity term. And if I set beta 1 to 0, I recover that second equation. And if I turn beta 1 of 1, I don't get that, but it's really turning this into the future. So I've taken this term, I basically converted this into this because I think this is going to help us apply some cool numerical methods. The method is called the Newmark's numerical method to solve these type of equations. Again, there's 3 unknowns. These are the unknowns. I don't know that the deflections at the nodes and I want to find out what these deflections are as a function of time. That is the question we're trying to answer. Don't forget that. And so let's look at what this equation here, mass matrix times the acceleration term vector plus the stiffness matrix times the deflection vector equals force. Let's look at how that looks like in the future. So if I look at mu double dot, pretend t is the present. If I look at how that looks in the future, this is what I got. And this is this is true. It needs to be true over time. So what I'm going to do, I'm going to substitute u double dot t plus delta t, and I'm going to substitute ut plus delta t, and I'm going to substitute what this is. So this is what I had the approximation for u dot, and my plan is to substitute it into this equation. So this term is this one on the left hand side, k times ut plus delta t. We've replaced that fully by this whole term. You can see that here. I've done that, fully replaced. And this is equal to f t plus delta t. So now you can see that I can solve for acceleration. Why? Because here you have u double dot t plus delta t. That can be brought up here, so I can factor it out. And the rest of it can go to the right hand side. And this is all function of time, present time. So if I know the acceleration at the present time, the velocity at the present time, and the deflection at the present time, and I know the force, the driving force in the future, I should be able to tell you what is acceleration. Because I know the stiffness, I know the mass matrix. And this is a time step that I'm looking at. Beta 2 is a parameter that can be specified in the Newmark's numerical scheme. So beta 2 is fully known. That's just a parameter that you specify in the Newmark's numerical scheme. One of the beta parameters you could use is beta 2 equals 0, okay? So how does Newmark's, and notice how I may not have used this middle equation. That's going to come up handy very soon. So what is Newmark's procedure? I'm going to use this equation here at the bottom over and over. So let's see how this works. At t equals 0, I'm given the stiffness. I know the stiffness of the mass matrix. For example, here, I know the mass matrix and the stiffness matrix for this system here, for this two-element system. So this is fully known, and this is fully known. That is not changing. So that's good news. So I know that stiffness, mass matrix, you definitely want to have some sort of initial velocity provided, some sort of initial deflections provided, and based on that information, you want to calculate the initial acceleration. And this is how you do it. You know the initial deflections. You know the initial velocities. So this is the equation I have. This equation has to be true. We discussed that before. And so I can solve for u double dot. I know the mass, I know the stiffness, I know the initial deflection, and I know the force at time is equal 0. So I should be able to calculate the accelerations at time equals 0 to make this happen, to allow the system to be in equilibrium. So now I'm going to calculate, what I really want to know is how things change over time. So let's look at time equals t1, like a little bit further away from time equals 0. So how do I go about that? So I basically use the Newmark's method. So I'll use this equation here at the bottom. I'm sorry, I went ahead of myself and I'm confusing you. So let me step back. So we're going to use the equation here at the bottom, the Newmark's method equation, and I'm going to plug in what's going on at time equals t1, and that's what I'm interested in. So to calculate u double dot t1, which is really what I want, since my previous time step was time equals 0, then these are all 0 here. So 0, all that, plus ft1, right? And so delta t is the time step. In this case, the time step is t minus t. So t1 is your delta t in this case. So delta t is known. Beta 2 you selected based on the Newmark's beta procedure, whatever beta 2 you want to use. I'll show you that later. M bold and K bold are fully known. U bold is known. U double dot is known from here. Dot, the velocities are known. Delta t is known. So this is all known. Okay? So that's the good news. So once I have this, and I have this because I know what forces I'm applying as a function of time. So this is known. I can now solve u double dot from here. I can solve u double dot from here. And once I have u double dot from here, I can now calculate the deflections and velocities at time equals t1. Why? Because the deflections at t1 are equal to the deflections at time equals 0 plus the velocities at time equals 0 times this step. the time step, plus 1/2 time step squared. So I'm using is the equation we had here at the top, which is your Taylor series expansion, but the glorified version. U double dot, the accelerations is known from this step, and I know the accelerations from this step here. So this is all known. So I know now I have marched the solution forward, and I know that deflections at time equals t1. Now, based on this information, I know the velocities too at time equals 0. I know the accelerations at time equals 0. I know the accelerations at time equals t1 because I calculated from here. Beta 1 is a parameter from Newmark's method. So this allows me to calculate u dot at time equals t1. So now I know that deflections and velocities at time equals t1. That's a good news. I was able to march the solution forward. So what happens if you want to time step a little bit further? Time equals t2. So time equals t2, again, we can calculate the acceleration again. I will look at time equals t2. Delta t here is t2 minus t1. So I went from t1 to t2. So your delta t is your time step here, which is t2 minus t1. So this is fully known. M bold is known. K bold is known. Beta 2 is a Newmark method parameter. So all this is known. All this stuff was calculated already. I found the deflections, the velocities, and the accelerations, and I know the force moving forward at time equals t2. I know what the force is because that's what I'm applying. So all this is known. We found that from the previous time step. So from all this information, I can invert this to get u double dot at time equals t2. Once I know this acceleration at time equals t2, I'm then ready to find the velocity as well. I know the velocity previously at time equals t1. I know the acceleration at time equals t1. Now I know the accelerations at time equals t2 because I solved it here, and that allows me to find the velocities now at time equals t2, the present. We can now calculate also the deflections. I know all this. I know the deflections at time equals t1, the velocities at time equals t1. I know the time step, which is t2 minus t1. And I know the accelerations, which I calculated in the previous time step, and I know the accelerations from this time step. So I know all this information, and now I know the deflections and velocities at time equals t2. Now continue to repeat the process over and march the solution forward. Here are some particular values of beta that will actually give you different types of methods. The explicit scheme is beta 1 equals 0, beta 2 equals 0. You have the backward difference, you have the Galerkin method, you have the central difference method. A lot of different techniques are available, but you just have to select the value of beta 1 or beta 2 according to this table. And you do have stability, so you have a conditional stability where the solution will be conditionally stable if the beta 1 and beta 2 you select is such, so the beta 1 and beta 2 you select here, when you plug it in here and the maximum eigenvalue from your stiffness and mass matrix is plugged in here, when you calculate this critical time step, if your time step is less than this critical time step, then you're going to have a stable solution. And so it will be conditionally stable as well. So in other words, if you keep your time, you maintain your time step less, you're pretty much going to converge the solution. You're going to have unconditionally stable if beta 2 is greater than beta 1 and beta 1 is greater than 1/2. So I won't go into the mathematical theory of this because that's not really what I want to accomplish today. And again, I have a YouTube video that goes into a lot of detail on this. So going back to the problem that we had at hand, and I took a little break because my point was to show you a few things here, right? So let me step back. I had this highly complex elastic bar partial differential equation that varied, where the deflection varies spatially and over time. And my goal here is to solve that in a simple way, in a systematic way, because finite elements gives you a systematic way of doing it. What we've done is we've discretized the deflection, which is continuous variable, into discrete elements. So we discretize this domain into 2 discrete elements. And as a consequence, I've discretized the deflections into 3 nodes. And in between, I have an interpolation function or an approximation function of that deflection. And what I've really done is I have discretized that partial differential equation, and I've turned the problem into a linear algebra problem. And what I was trying to show you here is how to solve such equation numerically, okay? And that's what I just did. And we're going to demonstrate it now for the elastic bar problem we talked about. So I'm going to go ahead and march the solution for this. But before I do that, I want to impose the boundary conditions. So we know the deflection at u1 is 0 because it's fixed on that end. So since the deflection is 0, the acceleration is also 0. So as a consequence, you can then eliminate the first equation. It's not doing much for me because I already know the deflection's there. And so we can just focus on the bottom two equations. And so I get this equation now, and these are the only two unknowns. So we've basically eliminated the first equation because the deflection is known. I don't need it. And in fact, I can see here that it doesn't matter. I can look at the second and third equation. In fact, many people get confused about what you're looking at here, but these are three equations. That's what matrix notation is. If you multiply this row times this column, you get 4 times u double dot plus 1 times u3 double dot, and then so forth. So that's your second equation. You can see here this 1 times 0 is doing nothing. And so I can just focus on the last two equations. It eliminates the first column altogether. And so I just have this square here that matters with these two vectors here. And so that's what I got. Now note that I don't have any force. No force has been applied to U2. Let me take you back to the original problem. And sorry for going back and forth. U1 is 0. No force is applied at this node, but we are applying a load at U3, which is an instant force of 1,000 pounds. And so that's why you see corresponding to U3, you have this force applied. And this is your harmonic force that we're applying. It's periodic. It doesn't look periodic, but if I use Fourier series to approximate that flat curve, it is periodic. And in fact, you're going to see that the response of the system is also periodic. We're going to see that very soon. So I have imposed the boundary condition, the spatial boundary condition. Now we're going to use the Newmark beta method to solve for the deflections and velocities and accelerations as a function of time. That is the goal. So the first step is to determine the accelerations at time equals 0 because there's no deflections and velocities at time equals 0. As a consequence, I know that the deflections are 0 here. We talked about that. That's what the problem statement stated. And I want to apply a force of 1,000 pounds. And given this information, you can then find the accelerations fairly simply by inverting the mass matrix in this manner. And then all this is known. And so you get the accelerations. And so these are the accelerations required so that there's no deflections and velocities occurring at time equals 0 when loads are applied suddenly of 1,000 pounds. In other words, I need this to occur for the system to be not moving at time equals 0 at all if I were to apply 1,000 pounds force suddenly at time equals 0. So once I know the accelerations, I want to use a Newmark beta method to estimate the acceleration. And so the next, I want to use a time step of delta t of 1 times 10 to the minus 5. And I want to use the beta 1 or beta 2 of 1/2, if that's okay. So we're going to calculate the accelerations in the very next time step from the following equation that we saw earlier. So I know the deflections at time equals 0, the velocities at time equals 0. I just calculated the acceleration at time equals 0. I know delta t, and I know what the force vector is, which is 0 and 1,000. Time equals 1/10 to the minus 5. This is 0. I know delta t. The accelerations were just calculated here at time equals 0. So I know that. So I can calculate the accelerations in the very next time step. So I've marched the solution forward just a little bit. You can see they didn't change very much. The accelerations didn't change very much, but I still calculate what that looks like. And so now that I know the accelerations at the previous time step, I know the accelerations at time equals 0. So I know the accelerations at this time step, and I know the accelerations at time equals 0. I can then go ahead and plug it in here. Beta 2 and beta 1/2. Beta 2 was taken as 1/2. So I can I know delta t, I know u dot, I know u. So then I can get the deflections at time equals 1 times 10 to the minus 5. So all this is known. The velocity is also known because I know the velocity at time equals 0. I know the acceleration at time equals 0, and I know the acceleration at time equals t1. And so once I have all this information, I'm able to then calculate everything I needed for time equals 1 times 10 to the minus 5. You can see a lot of computations that need to be done. And this mass matrix here, this calculation has to be inverted. You have to invert this too. So using this new information that we got, we can calculate accelerations in the very next time step, 210 to the minus 5. So again, plug in here the stuff from the previous time steps, and then the force moving forward. So the present now is 2 10 to the minus 5. I know that's what that is. And now I can solve for the accelerations from this by inverting this not mass matrix, but this formula here, which will turn into mass matrix if beta 2 is 0. So doing that, I'm able to find accelerations. Once I know the accelerations, again, I can find the deflections and velocities at this particular time step. So now repeat the process and keep marching the solution. This was done in Mathematica. My purpose today is not to teach you Mathematica, but why don't go ahead and pause the video and see how I went about it. In fact, go ahead and see if you can even program it in a different program like MATLAB and basically time march the solution. I have a do loop here that basically runs through the Newmark beta method and solves for the deflections, accelerations, and velocities as a function of time. And here you're going to see that I use all the same parameters in the example problem. I can then plot everything. In this case, the end deflection is what I'm plotting here. And you can see the solution is periodic. You can see here that you have this one here is repeating, these characteristics are repeating. This is repeating here. And this part is repeating here. So clearly, it's a periodic response due to this instant force that's applied that's kept constant. And there's no damping, so it's going to continue oscillating forever. Which know that if notice if you apply damping, it's going to die out, potentially. How to implement this into Abacus if you were to do it by hand? And again, this is not a finite element class, but it is worth trying to explain to you what is the brain behind stuff. So here's how you define the nodes. For example, you define the elements here. Here's where you apply the material properties. In this case, we have a truss element. So this is the element that was selected. We have two elements labeled 1 and 2, which have nodes that connect. Element number 1 connects nodes 1 and 2. Element number 2 connects nodes 2 and 3. The coordinates of nodes 1, 2, and 3 are given here. The modulus is given here, the Poisson ratio here, and the density here. And then you have the amplitude of the load applied, which is at time equals 0, applied 1,000 quickly, and is held constant over time. The initial the velocity is 0. The initial velocity is 0. You also have the boundary conditions, and then to run the analysis, basically, you're going to use a star dynamic to try to replicate what I have done. The problem is it doesn't match. So do we make an error? Did our analysis, which was done in Mathematica, and it's the dashed line, done incorrectly because it does not match the Abacus solution? Well, it turns out that our analysis is actually more accurate than Abacus in this instance. The reason for that is that I want to explain why that is in a second, but I want to point out something more, is that Abacus uses the Hilbert-Hughes-Taylor method, HHT, numerical integration. And I want to point out that the Newmark beta method is a special case of HHT. So HHT is a method that improves the numerical dissipation for high frequencies without degrading the accuracy of the solution. So you can time march it without losing a lot of accuracy, and it eliminates some of the numerical dissipation, or it improves the numerical dissipation that occurs at high frequencies. So that's why HHT can be very useful. The main difference with Newmark beta method is the following. The Newmark method is a special case of HHT by setting alpha equals 0. So again, if everything I've done is with the Newmark method, and if you set alpha equals 0 from the HHT, you recover the Newmark method. But the reason it was not matching is not because I did not use Hilbert-Hughes method. It actually has to do with something called mass lumping. So Abacus, to make everything more computationally efficient, what it did, it actually looked at lumping the masses. I'll explain what that is. So if I look at the mass matrix, it took 2 and 1 and put them all into the diagonal. So 2 plus 1 is 3, 1 plus 4 plus 1 is 6, you put it in the diagonal, and 1 plus 2 is 3, you put it in the diagonal. So the mass matrix was actually diagonalized, and it actually improves efficiency in the calculations in some ways, but it actually reduces the accuracy a little bit. So the new system then, if we do what Abacus did, which was to lump the masses into the diagonals, you're going to see that I can now solve for the deflections, the nodal deflections, using the Newmark beta procedure. And if I did that, you're going to see that even though I used the Newmark beta method as opposed to HHT, I was able to match the solution in Abacus. So Again, I will not consider this solution to be way off by leaving the mass matrix alone and not making the modification. The dashed line is Mathematica, and this one was done without modifying the mass matrix. I will not consider this too different from the solution we got, but it does demonstrate there is a small amount of difference when you go to a lump sum mass matrix. We can also look at the problem of a beam. And so I want to go ahead and I don't want to bore you through the details on how to discretize the beam problem. In this case, the beam problem is one where the beam can deflect transversely. So before we looked at the axial motion of a bar, now we're looking at how this beam can deflect out of plane or in a transverse direction due to loading applied transversely to this bar. And so again, very similarly, we can discretize this equation into using the weak form Galerkin. We could discretize this using the weak form Galerkin, as we discussed earlier, but I don't want to go through this level of detail. The bottom line here is that when you discretize it, you will get the stiffness matrix and the mass matrix that corresponds to that system that we just discretized. So the bottom line is that by discretizing the stiffness matrix and mass matrix, I'm able to simplify the problem once again. I'm able to get the mass matrix and stiffness matrix in a very similar way I did it for the axial bar problem. So very important to see how we've done that, how we converted a very complex problem into a linear algebra problem. And so now the approach is that I've taken that very complex equation, turned it into md double dot plus kd equals q, and I've accomplished a lot by doing that because I've simplified it. And so now I'm ready to study a new problem. And this problem could be, hey, just use one element to solve it. And the idea here is consider a clamped beam. So the beam is clamped, meaning the beam is on the left-hand side, is not allowed to have any slope, and is not allowed to move. This is a governing equation for the problem, and we're going to apply the following loading, distributed load, on the whole bar beam that looks like this. We're applying a loading of 100T, so it's increasing over time and is linear, and it's going to be applied at that rate, at this loading rate. And another thing we want to point out is that at time equals 0, the deflection at the very end of that bar is set as 0.2. So we're applying a small amount of deflection at the very end of that bar, at the very beginning, time equals 0. I also want to point out that at x equals 0, which is where the clamped condition is, the deflection and the slope are 0, and that's true at any point in time. So we're going to use a one-element solution to try to figure out what is going on with the system. We're going to assume that the beam has 0 initial velocity and acceleration to solve this problem. So very simply, I have this dynamic beam problem. The mass matrix, V here corresponds to the deflections at node 1 and 2. And these are the slopes at node 1 and 2. Remember, this problem is a single element. Node 1 corresponds to the clamped end. Node 2 corresponds to the other end. So here's a stiffness matrix. And then here is the vector of unknowns, deflections that are unknown. And here is the distributed load that we talked about. And also then you have these loading conditions. These are concentrated loads that you could apply. So here, you notice here how the velocity, the acceleration is 0. The slope is also, the second derivative of the slope is 0. And then you also have that this velocity, not velocity, I'm sorry, this is not the velocity, this is deflection, is also 0 at node 1 because it's clamped. That's why that's 0. So these two are 0 because it's clamped, and these two are 0 because it's clamped. Does that make sense? So that has to be the case. Because it's clamped, remember, 1 here, the subscript here 1 means node 1. And node 1 is, if you have a single element, think of an element of a bar, at the very left, that node is clamped. And so it is not allowed to move, and there's no slope. So that's why these two are 0. And so then I'm left with basically the bottom two equations again. So this bottom, this 2 by 2, and these two are the only unknowns. So I've simplified the problem to that. Now what I can do is substitute what I know is that I told you the accelerations are 0 at the beginning. We told you that the deflection on the right hand side is 0.2. We specified that. and that we didn't tell you anything about this one. And then we have this equation, these two equations. So the only unknowns then become theta 2 and q3. And so I can solve for theta 2, basically I get 0.015. And so I'm able to calculate the rotations at the other end of the beam. Remember, subscript 2 here is the node 2, which is at the other end of the beam, the right-hand side. And node 1 is where it's clamped and it's fixed. So now I'm ready to use the Newmark beta method, use the same procedure. I know time I was ti. I know exactly all these numbers. I know the forcing function as a function of time. I can then find the new accelerations. Once I know the accelerations, I can then plug it in here and then solve for the deflections. Once I know accelerations, I can also find the velocities and then repeat it over and over. You can see here how I've done this in Mathematica. Feel free to pause the video so you can see how this was done, but it's basically the same procedure I discussed before, but with the axial bar. Again, to implement this is very simple. This was done in Abacus again. Same process, but now we use a beam element because a beam element is meant to analyze problems where the beam is fairly long along the other two dimensions and it's going to take transverse loading. We applied a static solution at the very beginning with that initial deflection applied, and then we stepped into a dynamic procedure to solve the problem. And after doing that, you can see how Mathematica does very well against the Abacus solution. And as you've seen so far, the calculations can be fairly expensive. I want you to notice something very interesting. Take a whole rocket. Let's take a whole rocket and say that I have an equation like this. And this equation has to be solved for the whole rocket, and perhaps the rocket has millions of degrees of freedom. Assume I have millions of elements to represent the whole rocket. This was a simple in this case, this was a simple problem. I was looking at a beam, single element, right? But assume now that I'm looking at a very complex system, like a rocket. And I want to solve this PDE, this partial differential equation, over time and spatially for a whole rocket. You can see here how this problem can become very computationally expensive. I may have a mass matrix here that could be millions of degrees of freedom. I have a stiffness matrix here that's millions of degrees of freedom. It's going to have, it's a square matrix of millions of columns and rows. And I have to invert this every time step. And that's going to be very expensive computationally to really do. So it's not practical. And so that's why I want to turn into the modal analysis. And so we discussed already the modal analysis. This is a free vibration problem, the eigenvalue problem, and is used to determine the natural frequencies and mode shapes. We talked about that. And so what we really want to do is to use these mode shapes. If I know the fundamental modes of vibrations of a system and I can use that, can I be successful at simplifying the problem just a little bit more? So, we talked about, and so that's why I want to really discuss mode shapes right now, because I want to first discuss that to kind of build the foundation for solving this kind of problems, which is we call this the direct time integration, and which is very expensive computationally. I'm trying to find other ways to solve this problem. And so I want to look at the basics here. So we're going to look at the modal analysis. Allows me to get natural frequencies, and it gives me the mode shapes. And I already discussed what a mode shape is. It's a shape the structure is going to take when it's vibrating at that particular frequency. The frequency, again, the natural frequency is really how many cycles per second that structure is vibrating if it were to vibrate in that motion. And so my end goal is to use this idea to solve transient problems. And I'll demonstrate this a little bit later. The motivation for free vibration problems, however, can be used for many other things. You can verify stiffness requirements. You can validate finite element models. I'll discuss that later in a future lecture. You can assess the dynamic interaction too. You can look at the changes that occurred to the system due to a design change. So you can evaluate design changes due to that. You can actually even use it as a structural health monitoring. Say that there's cracking in the system, well, the stiffness has been degraded because there's cracking. That's going to shift this DNA that we talked about, and those frequencies will be shifted because the stiffness changed, and the frequencies depend on stiffness, so you know that cracking or something happened to the system. We can use it in a transient response analysis, which is my end goal in this particular lecture. And also we can use it, and I discussed this earlier, we can ensure that the frequency of the structure does not operate near the resonance when a forcing function is present. I invite you to look at the Tacoma Bridge failure as an example. And then I talked about damage detection. So getting natural frequencies and mode shapes, doing that process, just trying to do that, is called a modal frequency extraction procedure. That's really what we're trying to extract the mode shapes and natural frequencies for a particular system. And so here's the plate as an example that I have given earlier. And these numbers are given in hertz. And the point I want to make is that these are fundamental shapes that the structure can take when it's vibrating at a particular frequency. So these really define, these are basically, I call it the backbone or the fundamental frequencies, the frequencies that are going to play a role in describing the motion of a system. And hopefully the motion of the system is really made up of these mode shapes superimposed in some ways. Perhaps when the system is in motion, perhaps when that happens, for example, it could be a combination of some of these modes. Note that when you do a mode, when you get a mode shape, when you do a mode shape extraction procedure, the amplitudes tend to be arbitrary. I'll explain why that is, and it has to do with the fact that this is an eigenvalue problem. Why wouldn't I examine and remind you a little bit about the basics of some of the vibration problems that you could encounter? So let's say we want to solve this free vibration problem of a beam. And again, every time you're working on frequency extraction procedures, we're talking about solving the free vibration problem. So here's your mass times acceleration term. This is the beam deflection equation that you may have seen. And so to solve this, we're going to do a separation of variables, Wx ei omega t. And so I'm going to plug this into this equation here. Ei omega t can be, that's never going to be zero, so that you can cancel that out. And then from here, I'm able to get a differential equation on W of x. So hopefully that's clear to you. I have divided this equation by Ei and Ei omega t, so you get this simpler differential equation. If I call this term right here like this, lambda equals this to the 1/4, we can assume a displacement solution of this form. So again, my goal here is not trying to show you how mathematically to solve things, but keep your big picture perspective active as you go through this with me. So the deflection assumption, the displacement assumption, which this is exact solution, by the way, is going to look something like this. Sorry about that. For a free cantilever beam, you have the deflections at the left-hand side is 0, and there's no moments applied on the right-hand side, or loads applied, because it's a free vibration problem. So the moment is 0, and the shear applied is 0. We have nothing applied. It's a free vibration problem. And so as a consequence, we can use these boundary conditions to solve for this constant C1, C2, C3, C4. And so I can put this into a matrix format and I get this. Now you can see here clearly that the trivial solution C1 equals 0, C2 0, C3 0, C4 0. If that's the case, then the beam is not moving at all. Nothing is happening. Another solution is driven by this matrix here, and we call this the eigenvalue problem. If the determinant of this matrix is equal to 0, then we have found another way of making this equation equal to 0. That's another way of doing it. So if I find the determinant of this matrix, I'll find that the characteristic equation that makes this determinant go to 0 comes from this particular equation. And I invite you to do it at home. It's very simple. Like sine of 0 is 0. A lot of this stuff will go to 0. It will be simple for you to find that the determinant of this matrix is this here. And you can actually find the solutions to the roots to this formula here in Excel or something like that. And you get this as the potential values that solve this. And notice how there's infinite number of ways of satisfying this. In fact, there's infinite number of values that could satisfy this. For a free cantilever beam, we have infinite number of eigenvalues. And the eigenvalues, omega I, and remember, lambda here is this here, right? Rho is a density, A is the cross-sectional area of the beam, E is the modulus, I is the inertia. So all this is known except for omega. L is the length, so that's also known. So you really, when you solve for lambda L here, the only real unknown is omega I. And so you can see here how I can have infinite numbers omega, and that omega is equal to this. I invite you to pause the video and show that. You should be able to show that omega is this, and that you're going to find that the frequency, and that this is a formula for frequency we talked about before, and there's infinite number of frequencies. And so the good news is that I could discretize this equation again. I could discretize this equation again using the idea of weak form Galerkin. I already went through that. But this time, for the time domain, I'm going to plug in phi e I omega t. So again, I don't want to bore you with the mathematical aspects. My point is that you can take this equation here and discretize it so it has the idea of the mass matrix like that. This is going to give you a mass matrix and a stiffness matrix. And so that's the point I want to make. You get a mass matrix, right, like this, and a stiffness matrix. I have discretized it for, if I take the domain of a clamped beam and turn it into a single element, I get a mass matrix and a stiffness matrix. I can plug in the boundary conditions. In this case, the deflection at node 1 is 0, slope at node is 0. You can then show that the system reduces to these equations here because V1 and theta 1 is 0. So you can basically simplify it further, and you get this as a consequence. You're going to find that the determinant of this, the determinant of all this, will give you the characteristic equation we're looking for, so we can solve for omega. And so pause the video and go through that yourself, but you're going to find that omega is going to turn into a frequency of 81 hertz and a second frequency of 794 hertz. So very simple process there. And so the point I want to make is that notice how we have discrete number frequencies. Because I have a single element, I can only calculate 2 frequencies, not infinite number of them. So I only have 2 mode shapes I can actually plot. 2 frequencies corresponds to 2 mode shapes. There's nothing more I can show because I've discretized a continuous system. I've taken this system right here, which we showed that it could have infinite number of eigenvalues and mode shapes, by the way. And by discretizing it, and I don't want to go into the details on how the discretization works because that's what finite elements course is about. And I'm just giving you a top level view on what's going on. I've discretized into this way, and there's nothing more I can do. There's only 2 frequencies I can calculate because I've discretized the system. And notice how if V2 and theta 2 is 0, I get the trivial solution. So that means the beam is hardly moving at all. There's no movement. Now that we know the eigenfrequency, we can determine the mode shapes. So for each frequency calculation, you can calculate the mode shapes that make this happen. So you can find the eigenvectors or the mode shapes for corresponding to each of these frequencies, omega squared. You can now plot it. For the 81 hertz, the beam is going to bend this way. To the 784 hertz is going to bend that way, meaning they were to plug the beam, you know, it is going to potentially vibrate at 81 hertz in this manner. And at 784 hertz is more likely to take that shape if it's vibrating. So the observation here is if we have 2 degrees of freedom, we can only calculate 2 eigenfrequencies and 2 eigenmodes. A system with n degrees of freedom will have n eigenfrequencies and corresponding n eigenmodes. The eigenmodes will have arbitrary amplitude. The amplitude is not known, only its shape. And the dynamic characteristics of the system are defined by these eigenmodes and eigenfrequencies. Again, there's no way that can calculate V2 and theta 2 in an absolute way. So I'm stuck at just finding something that can be plugged in and that relates V2 and theta 2. So the arbitraries are basically arbitrary. If I go and use a 20 element discretization, I'll get a stiffness matrix that looks a lot more extensive, a mass matrix that looks a lot more extensive. And you can see here how a 1 element solution, the first mode matches really well. The second mode doesn't match very well. For 20 elements using our own models in Mathematica, we got really close across the board. You can see that here, but it can only get 40 frequencies probably. Well, the analytical solution can get infinite number of them. So that's the point that I want to make sure you understand, is that When you discretize a system, you have taken a continuous system and discretized it, so you have a finite number of subdomains, and that, as a consequence of discretization, also turns the problem into a finite number of eigenvalues and mode shapes. So it's an approximation of the system. In Abacus, to perform an eigenvalue extraction procedure, you define the nodes, the elements, and then you provide the material properties, and then you simply calculate the frequencies with the star frequency command, and that will give you the frequencies of the system. Here, I'm plotting some of the mode shapes for 81 hertz. It looks like this is clamped here. This for 20 element model. You can see here that that's the second mode shape, the third mode shape, and as you go higher and higher mode shapes, in frequencies, the mode shapes look more and more complex. There's a very interesting mode shape, and it's the axial mode that you get as well. So Abacus, finite elements, and by the way, what I showed you here was not Abacus, this was analytical solution. This is Mathematica using our own code, 20 element and 1 element, and what I'm adding now is that Abacus solution is basically exactly the same as our own solution. My point being is that the solutions in Abacus, the methods we're using are basically the same as what Abacus is using. And so I hope that's clear. Pardon me about that. And so I'm going to use that to my advantage. I'm going to use the mode shapes and frequencies. So again, a system, a structural system is going to have fundamental natural frequencies and mode shapes that describe the way these structures will vibrate. And the natural frequency basically tells you the number of cycles per second the vibration motion is occurring. And so I'm going to use that to my advantage. I'm going to use a transient dynamic analysis now by using the mode shapes. If you recall, the transient dynamic analysis with direct time integration discretized the spatial domain using finite elements, and we have to solve for deflections, velocities, and so forth as a function of time. The benefits of what I showed you before on the dynamic transient analysis with direct time integration, the benefit of that is that you can predict the structural behavior due to time varying excitation. The transient load excitation is explicitly defined in the time domain. It allows for definitions of applied forces and enforced motions. You can also model nonlinear behaviors, contact plasticity, and so forth. But if you had 1,000,000 degrees of freedom, it's going to be very tough to really solve that for every single time step. This approach can be computationally expensive, very expensive, even for a linear system. So it may be more advantageous to take advantage of the fact that I know that the system is going to behave it's going to have a combination of some of these modes. If I can do that, I have done a great job because I have simplified the problem to some extent. And so that's where I want to move towards. The goal is to simplify the solutions in some way. So the mode shapes are essential in a modal transient solution. In a modal transient solution, our goal is to use mode shapes to determine the response of the system, as these define the dynamic characteristics of the system. In the previous example, each mode shape that we saw was of a size of a 1 by 40. And in that particular case, there's 40 mode shapes and 40 eigenfrequencies. But it is important to note that if I were to look at the deflections, and I were to think of these deflections to be as a function of time. So take the total deflection of the system, and let's make that total deflection of the system as a function of time to be a combination of these mode shapes. But perhaps it's a combination of all the mode shapes, perhaps. I'm using all of them. So, but notice how if I say the deflection is a linear combination of all these mode shapes, that perhaps there's a little bit of this, a little bit of that. Maybe it's mostly A1, this particular first mode shape. So maybe the deflection of this beam really depends on the very first mode shape, not a lot from the second or third. Or it's really a combination of all of them, a little bit of every of them. And so note that the mode shapes are known. We know the shape. We know the shape. I just don't know how much of each I have. And so if I say that the total deflection of the beam is a linear combination of these mode shapes with amplitudes that are unknown and they're a function of time, then perhaps I have a way to have simplify the problem. Think about it. And let's put these mode shapes, which contain these shapes, into this vector phi. And let's put these nodal coordinates, these nodal values of these deflections here as a function of time, these amplitudes, I should say, these amplitudes that tell me how much of each of these mode shapes I have into a vector bold A. So phi bold A is fully known, A bold is not known. So this total deflection here, bold, only depends on these amplitudes. So what I have done something very interesting. It may be convenient to use less modes in the linear transient dynamic formulation. So, perhaps my system, which have millions of degrees of freedom, their whole rocket have millions of degrees of freedom, in our work to determine the frequencies and mode shapes, I will also have millions of mode shapes and frequencies. We discussed that before. And then as a consequence, I'm going to have millions of amplitudes here. I know the mode shapes, and I have millions of amplitudes here that need to be found as a function of time. So not a lot of benefit. But what if I told you that the rocket is most likely to, the deflections and the response of this rocket is going to depend on perhaps a handful of modes, maybe the first 20 or 30 modes. Maybe it's not really going to have a lot of the higher order modes. And so I want to go back here to demonstrate what I mean with the plate. So say I have this plate here, and so for this particular plate, perhaps the modal response has maybe there's 400 elements here, so I have 400 mode shapes and 400 frequencies, and perhaps the first 6 modes is really what I need, right? So we're going to then think about modal truncation. The frequency content of the forcing function can perhaps be examined and can be used to determine what modes can be truncated. We talked about that before. If you have natural frequencies of the system, say you have a natural frequency that's about 30 hertz, but the forcing function is such that the frequency content of the forcing function is 1,000 hertz. We already showed you that omega f divided by omega n, if that value is very large, the contributions to the peak response of the system is going to be very limited. As a consequence, you can use the forcing function frequency content to guide decisions about where to cut off and what mode frequencies you should account for. And so going here, what if I say that the total deflection and the deflection of the system only depends on a handful of mode shapes, not the whole range of mode shapes and frequencies, but just a set of that, a truncated set of mode shapes. Why is that? Because we already stated that if the forcing frequency had frequencies that did not matter, I did not mean that, but say the forcing frequencies were very high compared to the natural frequencies of interest, then you can truncate the modes to only include the modes that you really need. And so, again, it's very important to consider that, to understand that. So what if we use a truncated set of modes? So I'm not using the full set, just a truncated set. So this mode shape here clearly still continues to be 1,000,000 degrees of freedom or more times the reduced set, okay? And A is the number of amplitudes that I really have to consider. So if I had, say, 40 mode shapes, but I'm only going to consider 4 or 5 mode shapes, then this vector of amplitudes here is only 5 of them in size. So 5 by 1, and then these mode shapes, I'm only considering 5 of them, so I have millions of degrees of freedom times 5. That's the size of this mode shape here. Now this is fully known, and A is not known. But what I've done is I've simplified the problem quite a bit. And so we had already demonstrated that equations of motion after finite element discretization can be written in this manner. We showed you that. So that's not new. But I also know that I know that D bold here, right? So these are deflections of the system. I've already shown you that D bold here is phi bold times A. Notice how R and R cancels out. You get n by 1. So you get the full information about every single node in your finite elements. You have it right here. It's fully known. And so you know how every single of those nodes of that rocket model, which is millions of degrees of freedom, you can find that here through this formula. So Again, but now I'm using a truncated set. And so how many unknowns I really have now? It's not millions of degrees of freedom. It's only maybe 3 or 4 amplitudes if I want to just use the first 4 modes out of millions of modes. So I've really significantly reduced the problem. And this is D equals phi bold A. Phi bold A can be substituted back here into this top equation, and I get this right here. What I'm going to do next is something that I call a mathematical miracle. It's a purely mathematical miracle, and it's what makes dynamics so exciting. What I'm going to do next, I'm going to pre-multiply by phi bold transpose, and that's a very bold move, no pun intended. Everything here is bold. I will multiply phi bold transpose here, pre-multiply. And when I do that, I get that these are R by N, and R is a number of modes I'm selecting, the truncated set. So if I have a million of degrees of freedom, I have millions of mode shapes, but I plan to use only the ones I think matter. So I'll use maybe 5. So this right here is 5 times millions of degrees of freedom. This mass matrix is millions of degrees of freedom times millions of degrees of freedom. And then this one right here is millions of degrees of freedom times the number of unknown amplitudes. And these are the amplitudes that need to be found that multiply these shapes. And again, I'm trying to find how much of these mode shapes I need. And that's what these amplitudes are telling me. And I will do that same here, and I'll do that same here. I get R equations. So I could have had millions of degrees of freedom here. I had millions of degrees of freedom, millions of equations here. And this mass matrix, millions of columns and millions of rows, but I reduce everything into maybe 5 or 6 equations. But not only that, I want to take this further and demonstrate something more. We have a reduced set of equations. For example, for the beam, simple beam example, I have 4 mode shapes. But if I were to use 2 mode shapes, and there are the main participants of the motion of the beam, and I decided that was the case, then the number of equations reduces from 40 to 2. And in the extreme case of a rocket, millions of degrees of freedom, maybe down to maybe 40 equations. And so that will introduce an error, and this can be addressed by looking at residual modes, which I don't plan to discuss here, but keep that in mind. Now, the mathematical miracle I want to discuss is quite incredible. The mass matrix and the stiffness matrix fully couple all the degrees of freedom. However, when I perform this pre-multiplication like that, it results in a mathematical miracle. And that's that every single one of these equations will be fully decoupled because of the orthogonality property of the mode shapes with respect to the mass and the stiffness. And here, we will assume that the damping matrix is such that it's decoupled fully. And you can prove that. I won't do it here. The bottom line is when you perform this particular operation, not only I had millions of degrees of freedom that reduced to 7 or 30 equations, which is way better than millions of equations, but further, I have decoupled them into 7 equations. I turn a whole rocket into mass and spring stiffnesses that are decoupled, fully decoupled. And I can now solve for these amplitudes. And if I know these amplitudes, then I know the mode shapes, I know the amplitudes, I know the mode shape, then I know how D, which is the deflection of the whole rocket, varies over time. That's what I call a mathematical miracle. One of the most exciting things in dynamics is exactly what I just covered. And so the other thing I want to point out here is that for a damped system, you can add this term right here. For the ith frequency, you can directly specify the damping ratio. You can specify that. If it's not available, you can assume 1%. It's a good approximation. Omega can be quickly be calculated, so that's that. So all this is known. Mass is known, K is known. This is known. It's fully decoupled now. A mathematical miracle. So C is known, and so you can now solve this uncoupled second-order differential equation using the Newmark beta method, which is extremely computation efficient. Now there's only a single equation you have to do the calculation I showed you before. Once you know the amplitudes, this goes into this equation. You know the mode shapes, so then you know the deflections as a function of time, and that's incredible. You can also look at the inverse relationships between the modal coordinates and the actual deflections. So if I know the deflections, I can try to figure out what is A in terms of D. That is very doable. You can do that. You can pre-multiply by phi SM bold, like that. And due to the orthogonality conditions of the mode shape with respect to mass, it turns out that this multiplication here is going to be equal to this right here. Okay, and so that's a mathematical miracle too. Let me make sure it's clear what we're talking about here. But if I pre-multiply by phi s m bold, and what I mean with s here is you selected a particular mode shape with that said number 3, mode shape number 3, or mode shape number 2, say. So if I pre-multiply phi 2 m bold to all this, what happens is that when this is 2, phi bold 2 m bold phi 1 bold, this goes to 0. The only one that survives is this particular one here because of the orthogonality properties we talked about. And, so then you can now go ahead and solve, because of that, you can now solve for A, the amplitude A corresponding to that particular mode shape, and you get this expression. You can also calculate the velocity term, and then you get that. So we can use this information to determine the initial conditions for the Newmark beta method, which is necessary to basically advance the solution. So I hope that's very clear on that particular process. And so I want to point out that these particular damping ratios can be specified and can vary for each frequency. It can vary. So it's important, you can measure these things. It's not easy to measure, but it can be done experimentally. There are other ways to specify damping. One such approach is called a Rayleigh damping or proportional damping. I recommend that you read this paper in the AWA journal from 2016 that discusses some issues with that approach. I think one of the best approaches is to measure damping and specifically providing that in the damping matrix. That can be more successful. So the analysis process flow is the following. You have a partial differential equation, you discretize the equation into a discrete number of elements, and you get discrete number of degrees of freedom. And what you want to do is calculate the mode shapes and frequencies for that system. You're going to have a discrete number of them, not infinite number of them, only because we discretize the continuous system. Get the free vibration problem. Try to understand the dynamic characteristics of the system, because that's going to be very important moving forward. The total deflection of the system is assumed to be a linear combination of these modes. And what we want to do is use a smart set of truncated set of modes. And we want to make sure that we use that in the transient simulations. How to determine the truncated set of modes? Say you have a forcing frequency of 50 hertz. You want to make sure that any natural frequencies, even beyond that, past that, is included in your assessment. But if you have something, a forcing frequency that didn't really matter for the problem, then let me backtrack again. I keep saying it incorrectly. I want to make sure it's clear to you is that you have a forcing frequency and you know the frequency content of that. You want to truncate past that forcing frequency. You want to be able to account for that loading condition. So I showed you how you can develop an uncoupled system of equations in the modal coordinate and how you can impose initial boundary conditions. And then you can use the Newmark beta method to really solve the problem. Once a solution is obtained, you can recover the deflections of the whole system. And again, just to show it visually here, think of this right here. Think of this being as millions of mode shapes and millions of amplitudes. And my deflection of that beam, what I'm saying is going to be a contribution of these mode shapes and amplitudes. But the mode shapes are fully known because you extracted the mode shapes in the previous analysis. So the only thing that's unknown is its amplitudes. So I simplify the problem from that perspective. The second simplification is that not all mode shapes contribute to the total deflection. It depends on the forcing frequency. So you have to look at that first. And then secondly, because of that, I have selected a set of mode shapes, not all of them, not millions of them, but maybe 7 or 10 or 20. And that has allowed me to reduce the number of equations that matter. I've reduced it from millions to 20 only. But by doing this pre-multiplication, I've proven to you that I have decoupled it to 20 mass, stiffness, dashpot equations that are decoupled from each other. Very powerful approach. And then we've used the Newmark beta method to really solve the problem. And we discussed the Newmark beta method in great detail earlier. Again, Taylor series expansion on U, Taylor series expansion on U dot, and then go ahead and review that back again to get a better understanding of that. So you can do this in Abacus very simply. Here's how you do it. You have a star modal dynamic procedure, and then you have to select the truncated set of modes. Here we selected 10 modes out of 40 for the beam problem, and I specify 1% damping for those first 10 modes. So that's a very simple process. And again, this is the same cantilever beam problem we solved before, but using the modal transient solution. And if you compare the solution I got using this, you will see that you will get the same answer than we did previously with the direct time integration, considering all the degrees of freedom, because there's no other way to do it. So the transient analysis summary is as follows. We discussed the direct time integration, and I showed you that can be quite expensive computationally. So we shifted over to a modal dynamic transient analysis solution approach. We want to make sure that the time step you select, so this is a lesson learned here, is chosen sufficiently small to capture the highest frequency of interest in the response. So if the highest frequency that you're interested is 100 hertz, each time period is 0.01 seconds. So you want to make sure you have at least 5 steps within that time period, which means that you should have a delta t of 0.002 seconds. The minimum preferred number of time steps is 10, is what I recommend. Very similarly, if your load input is selected to be 1,000 hertz, please provide at least 0.002 seconds of input to make sure you're providing sufficient amount of input to the model so that the model can respond properly to the inputs you're providing. If the inputs you provide to the model are too coarse, then you may introduce invalid dynamic responses that are really not existent. So we're going to dive into steady state dynamics using finite elements. We already discussed state dynamics earlier, but I want to cover how this would be done in finite elements. So if you recall, modeling the transient response is quite intuitive. You can see the time history of the event, but there is an advantage of trying to understand what is the system's behavior when you subject the system to a forcing frequency, and we look at it from the frequency domain. We try to understand what is a peak response due to that input that we put into the system. And so here is what we had discussed earlier, that as I vary the forcing frequency and I get close to the natural frequency, that you'll get a peak response. And as I move away, then I have less of a response. And so this becomes very important in the design of structures. As you recall, the force vibration response equation was given by this. If the right-hand side is 0, we call that a free vibration problem. In this case, we have a forcing input here with a frequency omega, and the frequency of the system is omega n, the natural frequency. So the forcing frequency is omega with the amplitude p, is a harmonic input. And we discussed earlier how you can input a Fourier series input. As long as it's periodic, it's a periodic input, we can call that harmonic. And this will cause an initial response, and that initial response quickly dies out. But what remains is your steady state response. And that's the part that we'll be discussing a little bit today, how to include that, how to model that in finite elements, how to determine what is a peak amplitude when I subject the system to this forcing function. Recall earlier that the deflection u is a function of omega. For example, if I make omega close to omega n, and I have no damping, this denominator goes to infinity, which gives you infinite peak response. So all systems have damping, so that is not realistic. If I have some amount of damping, then this here goes to 0, and then your peak response is dominated by this damping, or the quality factor. We called the quality factor earlier, is dominated by damping, as you can see here. And so we also discussed this plot here. Basically, omega f can be varied, say from 0 to 3 as an example. This ratio can be varied 0 to 3. And when this ratio is 1, I get the peak amplitude. And then when omega f divided by omega n is very small to 0, is close to 0, which means omega f is very small compared to omega n, then you get almost close to static response, because the amplification factor is close to the static value. And as you go closer to that resonant condition, that peak amplification increases. when you move away, which means omega f is much greater than omega n. And that means that you're vibrating the system like crazy, but the natural frequency of the system is perhaps 3 hertz. But omega f could be 100 hertz. Perhaps you're not really doing much by putting that input. And so that's shown here that you're getting very small amount of response compared to if you were to apply it statically. Okay. And so why we perform a steady state frequency response analysis is helpful for evaluating fatigue. As an example, we discussed that I could put a forcing frequency here or harmonic input. That will result in a steady state response that's also harmonic. And my point being here is you have to evaluate the fatigue damage due to these stresses oscillating. And so that's one reason why this is helpful. The second reason this is helpful is if you want to analyze to make sure the structure does not get into clearance problems. That's where this could be helpful. You can also use this analysis to design the system so you know what the peak response is, and then you can design around it. So for example, I could design it to be away from this peak response, and I can select my forcing frequency to be different from the natural frequency, or I can redesign my structure to modify the natural frequency. Or the other option is to work with the damping. You can see I have a lot of different options here, but the idea is to not allow these two to be too close to each other. But there are some cases where that's not possible. It's not possible to keep them apart. From that standpoint, from that vantage point, these plots become very useful because you can see what the peak response is. You can actually even apply this statically to a model to understand, hey, what is going on here in terms of stresses? So implementing this in the finite element solver goes back to the basics here. You have a partial differential equation, which is where the variables, deflections, are a function of spatially, and they're also a function of time, the time domain. And we discussed how that's so hard to solve. So we have to use finite element models because they discretize these partial differential equations and put them in a manner that can apply the ideas where the numerical ideas that we discussed earlier. So how we do this, we do a eigenfrequency extraction. You know, that's a good first step to understand the dynamic characteristics of the structure. Remember how we discussed that every structure has a unique DNA, it has its own behavior, and so it's very advantageous to understand that behavior so you can then subject that structure to the frequencies that you may see in real life. And that way you can understand what is going on with the response of the structure. We also are going to then take this information to then understand where to evaluate the response. Like, what is the point? If I know the natural frequency is here, doesn't make a lot of sense to be looking at out here. It makes more sense to be looking near the natural frequencies. And that's why getting that first step is so useful. The second thing you want to do is to sweep across a frequency range of interest, say from 0 to 3, and then you want to have enough data points near the natural frequency so you can get a complete response. What I mean with that is, if I have a peak here, I want to get enough points around it so I can create a shape. This shape, again, is useful for design purposes. Maybe you want to move away from that, but you don't want to be too close, but you can at least get some idea what's going on with the structure. Again, this y-axis here is telling me a lot about the dynamic amplification compared to if I had put the input as a static loading. So this is really giving me that idea of what's going on dynamically.